Welcome. This is Team 4, and we're presenting Seawalker.
Well, we have the product description. Well, for the needs, basically traditional low-cost small tractors lack accurate navigation due to the drift from the odometry, their limited sensing capabilities, and the dependency on a single location localization method. And without that reliable waypoint detection, the vehicle may deviate from its original path and will not recognize the boundaries. And because of that, it will lose operational reliability. And because of this, the needs are basically a multi-sensor system that detects waypoints, corrects post drift, and validates trajectory. And for the vision of our product, the Seawalker system aims to basically enable autonomous navigation for small agricultural vehicles by integrating encoder-based telemetry, waypoint recognition, and an external camera-based localization. The final goal is to provide a reliable, safe, and repeatable path-following capabilities that can be used as a foundation for precision agricultural research or educational development in embedded autonomous systems. And well, for the target groups, as previously mentioned, one target group is engineering students, and they will benefit from being able to learn a real industry-level multi-sensor integration, CAN communication, and embedded autonomous navigation. They also researchers in agriculture, in robotics or agricultural technologies will benefit from being able to use a platform to evaluate waypoint detection, position algorithms, and state machines in future tracking. And lastly, the last target group is the precision agricultural developers, which will benefit from being able to use a low-cost approach that follows the path without a high-cost GPS or commercial sensors. And well, for the proposed solution, the Seawalker is basically a mini tractor that follows the predefined lanes using the encoder-based telemetry while validating the waypoints with the camera. And the system uses basically a CAN-based communication between the ESP32, and it gets the information from the EMU and the encoder, and an STM32 microcontroller, which makes a decision based on the information that is transmitted to it. And the system incorporates an external camera-based location to assist the state machine, reducing the dependency on odometry while providing real-time trajectory. And also, we have a way to check the waypoints, which is with a LED that indicates we passed the waypoint. And some key features here are the CAN-based multi-sensor system, the autonomous navigation through segments, waypoint recognition, the camera localization, real-time feedback, and safety integration. And well, we have the breakdown of the tasks, and here we have, for example, the first task is the requirement and architecture review, which is basically to update the requirement diagrams based on the previous uploads. Well, the STM32, the next task is the STM32 controller and trajectory state machine, which is basically the main C code. The SP32 C3 sensing node, which is the encoder ISR, the acquisition from the IMU, and the transmission of the data to the respective IDs. Also, the camera-based localization through PLE, also the integration and system tests, the UML modeling and documentation, and as well the time representation. And here we have the Gantt style table, which indicates more or less how we had the time frame in which we worked in the stuff. For example, in week 11, I did the requirement architecture review, and then in week 12 and 13 and 14, Omar did the STM32 CAN trajectory. I also did the SP32C3 encoder plus IMU integration in week 12 and 13. And as you can see the other amount of work that we did throughout these last 5 weeks.
In this table, we see the collaboration of each team member. For example, Omar be the developer of the STM32 controller. pad to support the PWM configuration for ESC and steering and participated in a robotic debugging. Then Eugenia lead the ESP32 sensing node with the little encoder ISR, distance computation, and an IMU acquisition, plus scan message packing for these IDs, and contributed to requirements tables and UML diagrams across the different layers. Then Gilbin was responsible for the camera and PLD localization pipeline and its integration with the CAN network, worked on post filtering and fusion requirements, and assisted in designing the last solution architecture.
So here we have our contents diagram. For this diagram, we consider our system as a black box, and we establish all the external variables that could affect our system. In this case, we put the environment, which provides terrain and obstacles to our seat walker, the power source and charger, which provide the power, the operator to start, pause, stop the system, and the camera who provide the waypoints and the position and key. Then our system provides the telemetry, the position, the battery and the shaft to the base station number, and the trajectory on our LCD. About our deployment diagram, this is like the technical part of our system, what's inside our black box. First, we have the ESP. Okay. We have our ESP, C3 Mini, who sends the CAN message through a controller.
Let me come after. What?
So here we have our wall system, which is the seat walker. First we have like our ESP3 C3 Mini, which sends the information that the encoder provides through SPI to our controller and transceiver. Then the controller and transceiver send it to the CAN bus, received by our transceiver, which send the CAN TX and CAN RX to our ST M32H7. Based on this information, the ST32 calculates like the PWM for the steering and the throttle. The PWM throttle sends to the S, which regulates the current and power to our DC motor, and the motor again catch that info and sends to the SP32. ST32 H7 also has the steering circle, which is like the direction of our wheels, and that's the line.
Okay, just stop there. Wi-Fi is not really there. And you need to tell the ESPs are communicating over Okay, yeah. Just write down the name of the protocol and make sure you submit that text. Okay.
Then we have our team diagram. First, the operator will place the tractor at the start and power on the tractor system. Then the STM32 will initialize CAN, motors, timer, and LEDs. Then load the weapon list and path parameters. Then we jump to our SP32, which need the EMU, encoder, and CAN. Then we have our section of the position loop. We have we sample the EMU and encoder, the local poles X, Y, and theta. Then pack the poles into CAN frame and send it to our STM32. In this part, we have a section of our control loop. The STM32 receives the position from CAN, then obtain navigation state, and compute the control action. Then we update our motor with the PWM. This affects two parts of our system. The motion or hardware, because once we have the PWM, the motor moves, and the encoder generates another ticks. Then we have a decision. If the final waypoint is reached, the motor will stop and set the completion left, and that will be the end of our activity diagram. And if not, we repeat the control loop.
Puede ser todo el equipo, puede ser todo eso. features or system needed, so with the reason for each feature and the criteria for us to know if the requirement was completed. This allows us to track our progress during the different stages of this project. We won't explain every single requirement, but the main requirements for our system was for it to be able to automatically generate the path based on the waypoints, use controllers for the spin and speed of the system, the trajectory of our system crust, and using an LCD, and use signal lights when we cross the way.
And here we have the implementation of the STM3287. Here are the key functions. Guarantee, if it doesn't receive, it just keeps staying on a delay phase. And whenever it receives, it separates between the four IDs, which is 0x98, 0x100, and 0x120 for the data received from the Bluetooth connected to the ESP32 connected to a camera, what's in the camera. And here we have the distance handling, just the current distance. That was for the stage 2 and part of the stage 3. And here we have the trajectory follow, which is this machine, which is just a case of 4 switches. That was also stage 3. The motor control, well, this was to calibrate or to say like the one is full throttle forwards really fast, and another one was going backwards really fast. And the right is the function, this function uses this function to send the PWM. The 30% echo is the degree, it sends the pulse of the PWM to the server, and the PNF is to know if what in the beginning is sending, and to know if it's stuck in a if or in before this point. And this is the encoder reader, which is on the S32. Was just 2 APIOs to the encoder, 2 in the middle, green and yellow. And the census estimation, we have the encoder reader, which is just encoder _ count. And this estimation is just encoder count divided by 5 or 10, 5 or 50. And that's how we get the distance, and we send it to the ID equipment. We also got the ID position, which is just AX, acceleration X, acceleration Y, and acceleration Z. And we could also have the gyro, which comes from IU. Since another ID, we have the sending into the MCP. The delay is around 10 seconds because that's the delay we have to handle the loop of the S32. The TMG one, was just whenever we connect the S32 to a computer to see if it's actually sending okay. For the categories, as I said, this is supposed to be 120. This is 100. This is from the encoder. 99 to the acceleration, and then 98 to the gyroscope. And this is 120 for the data received from the other ESP32. That's connected to the computer. That's connected to the camera. And run down the case.
So the path that the tractor will follow was this one. Instead of going from the left to the right like the continue, it's starting from the right, goes to the left, as you can see, it goes straight. There's a turn and goes back down to the other side of the area. For this part, we did 2 test cases, which is going to be the stage 3, part 3, and the new part. So this is going to be the system testing part 1. So which in this part, what we wanted to do is the tractor has followed the path that we showed before, and the LED has to turn on when it passes through the waypoint. We need some steps so we can test if the system was working correctly. So in the initial condition, we made sure that the tractor was forward on, the SPC3 setting the encoder distance via panel. And the actual behavior was balanced. It was actually sending the correct packages, it wasn't sending any errors or Fs or it was sending the correct messages. Next, it was the start of the movement, the step 1, which the STM32 initializes the trajectory. The state machine reads encoder distance and commands ESC to move forward while keeping the steering straight. Again, it was okay. It was expected. It behaved like we expected. For the stage step 2, sorry, it was a waypoint reach. What we wanted to happen is that the system should turn on the LED as soon as it reaches the waypoint, and that actually happened. When it arrived to the waypoint, it turned on the LED and continued to the next stage. So it was from the first waypoint. It was step 1 done, and it goes to the next section. Lastly, the step 3 was the final waypoint and completely stopped. So when it reaches the final, the third waypoint, it has to update the next waypoint, going straight again. And when it reaches, the LED turn on, and it should stop, and that was the behavior that happened. So what we did in the other one is basically almost the same steps for the system. So what happened in this one, like the difference between each other, is this one kept the same path, like straight turn. And but in that one, what we did is put it like in the middle, and the tractor has to reach the waypoint. So it has to update its position or steer a little bit to go through the waypoint, depending on which position you're putting. So it doesn't matter if we start here, the tractor should go all the way here, turn. Or if you put in the middle, it has to go here. So that's what we updated. And we have two videos. I don't know where it's. So this is going to be the final stage. Should we see this? So this is for the final stage where it follows the coordinates. Okay, so what we're doing right now is we're testing right here. I'm just waiting for one more to finish saying the other part of the video because we sent two videos in the project. So right now we're just going to turn on the tractor. As you can see, here's one of the waypoints marked some black X. The tractor should move a little to the right, then turn to the left completely, doing like a U-turn.
And then that should turn on.
The body was running a little, so we have to push it. And it turned on again, and it kept going like a U-turn, reaching the next one that was here. And finally, going to the last one. As you can see, it didn't go straight, so in the last waypoint, you had to do a little bit of a right turn to reach the last one.
So this is the second one, right?
Yeah, that was the second one. And here is the stage 3, part 3 video. We did a straight turn straight. Those are the waypoints. The post-it notes were our waypoints for the last challenge in the stage. So it has to go straight to a left turn. As you can see, there's no steering. It's just one trajectory that is following.
So we also designed a little 3D model for the cabin of our truck, but sadly the impression didn't like finish in a good way. Like this would be an example of the cabin for a tractor. It's printed in 3D resin, but my 3D printer was like a little bad.
Okay. Yeah, good work. Okay.
So the simple P1 and STM32 system controller. Executed a data machine during trajectory only from the holder module mission.
Okay.
So as for final reflections, working with CAN-based sensing and sensor fusion and real-time actuation help us experience industry-level embedded development rather than isolated main control exercises. And the project also taught us the importance of deterministic communication, safety constraints, and coordinated hardware and software design when building autonomous systems. And the Goggins physical behavior and the tracker demonstrated how theory, code, noise collaboration, and mechanical limits must be all aligned to achieve real autonomy. We also learned the value of documentation and UML modeling as tools that guide implementation and multi-phase systems scale. And we think that the Monterrey for advanced embedded system course professors and Johnny for providing access to the necessary tools, guidance, and space to explore real-world engineering challenges in autonomy and precision agriculture. Right, that's it for the presentation. Now we can go to the real-life demonstration.
Okay. Very good. No, I think the general points, same thing as we mentioned in the other, when presenting the CAN database, just write the IDs, but specify as well the position. If you were sending like spline and answer from the camera, then X is using by 1 and by 2.
Okay.
Probably.
Yeah.
I think we should specify that. Other than that, very good work. And so, how do we proceed to the demo? You want me to we give you more time?
Yeah, you can give me 20 minutes, I'll figure it out.
Yeah, okay, so that's